Bismillahirrahmanirrahim. Nahmaduhu wa nusalli ala rasulihil kareem. It's an honor and a pleasure to welcome you all to LUMS for our, I would say, mini course, short tutorial on deep learning. My able colleague here wants to call it as conversations. Let's see if this is really a philosopher's dialogue or something deep. So we were quite overwhelmed by the response to this particular call. Let me just sort of set the stage here. We are organizing 2 workshops back to back. One of them, the announcement for that, you can see here. This is the workshop on precision agriculture and forestry. This is an annual event that we organize mostly at LUMS, but last year it happened at Ali Institute. Has been going on now for the 4th consecutive year. Basically brings together the community from ICT and agriculture together. Then we have another event which is not mentioned here. That is the 15th workshop on field and agriculture, field and assistive robotics. That has been going on since 2011. And the tradition has been that within these events, we have been incorporating these student tutorials. And even this year when we were thinking about few topics for the tutorials, we thought that machine learning, of course, is a very important tool now, both from the perspective of precision agriculture, remote sensing kind of applications. It has really popped up as a thing to look into, but also in the robotics, of course, it has been heavily used, so we should pay attention to it. We were expecting that as in previous years, we would get like 15 students to respond, and we booked a small room. And I think last night, actually the 2 nights before, when the registration went to, I think 300 and something, then we had to do something about it. So we booked another room, and we had to limit the registration somehow as well. Some filtering that we had to do, but so unfortunately some participants that we really wanted to invite to LUMS couldn't be here. For them, this event is being video recorded, and we will put it on our YouTube channel, so please feel free to share with your colleagues or students who have not been able to make it. But really the hope was that in a very short while, in maybe 2 sessions or 3 sessions, spanning a few 3 to 4 hours, it is not really possible to give a deep introduction to a deep subject like this. And I think most of the coverage that I have seen on this topic is very shallow, unfortunately. And we also didn't want to go into implementation tools or how do I work with a particular library. What the objective here was, or at least which is what I conveyed to my the instructor here, was to basically give a self-contained introduction to a graduate student or a senior student to give some fundamental knowledge. Hoping that then you can carry on your own. So what is that little nudge that we can give you, and then you can carry on your own? So hopefully we'll be able to cover it in these 2 topics. In parallel, there is another tutorial which is happening on Monday. That is on vehicle dynamics. And in the same spirit, Professor Carsten Burns, who comes to us, visits us very frequently, he will be giving again a self-contained 3-lecture introduction on, well, how do you make self-driving vehicles, for example. Now, if I had called it self-driving vehicles, we would have received 500 registrations. But to go and look into what the mathematical aspects of modeling a self-driving car is, of course, that is much deeper. So that is a self-contained introduction to how do you model the kinematics and dynamics of a vehicle, be it a drone, be it a ground vehicle, and so on and so forth. So the response there, of course, is not as much as we received here. But this is okay. So I invite you to come to that other tutorial as well. If you have registered for this workshop, I think probably you would have registered for the other mini course as well. So that is the context. Let me just very quickly introduce Dr. Hassan Mohy-ud-Din. It's really a pleasure to invite him to give this mini course. So he is currently the director of the Clinical and Translational Imaging Lab, meaning that his main focus is on medical imaging kind of applications. An assistant professor at the LUMS School of Science and Engineering. He joined us a couple of years back. He completed his PhD and master's in electrical and computer engineering, and then another master's degree in applied mathematics and statistics from Johns Hopkins on a ECE JHU fellowship. Then he was a postdoc at Yale, again at departments of radiology and biomedical imaging at the Yale School of Medicine. He was a clinical researcher at Shaukat Khanum for a while, for a short while I would say, before joining us. He has won many prestigious awards. He's publishing very I won't say prolifically because I think that's not a term that we should be using. I mean, I think doing some very quality work. Won a number of awards, as I've said, the Bradley Alavi Fellowship, the Siam Student Award in 2014. He has been associated with a number of institutes here in Pakistan, including LUMS, before going for his higher studies. So it's a real honor and a pleasure to give the floor to Dr. Hassan Mohy-ud-Din, who would lead us through this journey into deep learning.
Thank you so much. Thank you so much. Assalamu alaikum, everyone. Am I audible to the intro? And I'll just make a request. I think there's a lot of space that is vacant here, so it's just a humble request. Yeah, they're really, really far. So
This is now a really deep network.
yeah, it's really deep. Yeah. Yeah.
Please come to the front layers.
Yeah. So even with my bionic vision, I can't see. It's very
But
difficult.
most of the interesting stuff happens at the front.
Oh yeah. Assalamu alaikum, everyone. Thank you so much, Dr. Abu Bakr, for this opportunity. And the reason I actually titled it as Conversations on Deep Learning is that, as he pointed out, that it's very difficult to fully do justice with such a profound course. And in a few moments, I'll try to prove this thing, that why this course is so profound. So we'll be talking about some subjects to see if we could go into as much detail as possible. And it is mathematical. It's immensely mathematical. So if we have a feeling that this course has nothing to do with mathematics and only programming, then I'm sorry, that's not a very judicious analysis about this course. So so this lecture will be split into parts. The first will be basically topics in machine learning, and I'll be starting with some examples, real life examples, where this machine learning and deep learning is heavily involved in current times, and trying to see that is there a valid reason that we should be studying this course, and is there some benefit to humanity that these techniques and algorithms are bringing to the forefront. And then we'll talk about supervised learning, unsupervised learning, reinforcement learning very briefly, and then we'll talk about a couple of tasks in machine learning, regression and classification. And then there's one important aspect of regularizations, and I'll contextualize it once we actually reach there. And then we'll move on to this topics in deep learning, where I'll try to introduce from a basic perspective this neural network, the most important algorithm back projection that made this deep learning thing really practical and pragmatic, that it is being utilized today. And then we'll talk about things that how we can enhance our neural network performance by various measures. To talk about convolutional neural network. I don't have a slide here. I'll just mention very fleetingly. So I apologize for that. And then there will be some very interesting comments that the deep learning literature is kind of publishing these days, which we have to be very careful. We don't want to be drowned by this tsunami. We want to be very wise about it, that what is actually the perks and of this technique, and where we should be using it, and what are the repercussions if we just follow it very, very blindly. So I work mainly on medical imaging. So it's basically I work on mathematical algorithms and techniques in medical imaging. So all my algorithms have a mathematical perspective, statistical, mathematical, machine learning perspective. But the overarching goal is basically clinical imaging. Although the concept of this workshop is robotics, but I'll try to make a connection, because most of the tools that we are using in clinical imaging comes from computer vision. And computer vision is a very fundamental part of robotics, because you ultimately want a robot to visualize the environment, to understand the configuration space. So he has to have some vision ability. And we use the same image-like or vision-like abilities in medical imaging, and I'll try to mention a couple of problems here. So very briefly about my lab. So I have two PhDs working with me, Temur and Sana Jabbar. I'm not sure if Sana is here yet. So we are working on brain tumor segmentation and cardiac image segmentation with them. And then we have Mohammad Faiziab Ali Chaudhry, who is basically a research assistant from UET Lahore, and Myra Afzal, and we are working basically on radiomics pipeline using techniques from deep learning and machine learning. And the funding largely from LUMS and SSC and LUMS, SSC and HEC and the planning committee. So before I begin formally, there are a couple of important announcements. The lecture has been drawn sources, a lot of material. I've kind of borrowed, or I'm happy to say borrowed rather than inspired from various sources that I'll be mentioning in my references. And as I said, so this course is quite involved. It's like an upper grad level course, and it is a highly interdisciplinary course. And to have a mastery of this subject, one has to have some knowledge of matrix analysis and linear algebra. Because when we're talking about things, when we are proving things, even when we're talking about computer vision and image processing, a lot of times we're trying to formulate our problems in matrix vector formulation. So we need to understand. And when you have matrix and vectors, you are trying to understand its properties. So linear algebra, the whole machinery actually comes into place. Optimization theory and algorithms, very, very important. I don't know of any subject which can survive without optimization theory and algorithms in current times. So whether it's robotics, economics, finance, any subject, speech recognition, machine learning per se, computer vision, medical imaging, even if you talk about mechanical engineering, you can't survive in research when I'm talking about like really cutting edge research. This is one of the most fundamental courses out there. And basic knowledge of pattern recognition, machine learning courses that has in a lot of universities. Obviously, when we're talking about random phenomena, most of the things that we are talking about are random phenomena, so probability comes for our help. Random variables and stochastic processes. So this is very, very important, and there are a lot of tools that we utilize. And I think a very, very conventional form of probabilistic analysis will show in deep learning today. Very, very important. So we want to understand what are these moments, how do we use these statistical perspectives, mean and variances, and mean over defined by distribution. So we want to use these tools, and this is very important. And as I said, the applications are quite wide, and they penetrate almost any field you can think about. And by no means these lectures or these sort of tutorials supplement a full course. They cannot. So you have to have these courses which are full-fledged semester-wide courses where you actually going through homework examples, exams, so that you are really going through the drill, so that you really master the concepts, the tools that you learn. So there's just a conversation. The title of the talk is like that. So we'll start with if you have any questions, let me know. So we'll do the questions at the end. Okay. So we'll start with machine learning. So the first example comes from computer vision, where I have seen and want to segment the objects in the scene. And that's what we call a semantic segmentation. Likewise, if a robot is actually like traversing an unknown environment, it is capturing these videos, it is capturing these images, and I want the robot to tell me what are the contents of that image. Are there people? Are there objects? Animate objects? Inanimate objects? Buildings? Whatever. So I want to segment. So these are different images, different scenarios, different configuration spaces, different open, closed door conditions, all sort of complexities that are constantly interacting in our daily routine. We see these images and we want to do a semantic segmentation. And I want to have as good of a segmentation as possible so that the picture, as they say, the picture speaks 1,000 words, I want to hear those words. I want the robot, I want the machine to tell me automatically, without any human supervision, what is the picture talking about. So that's what we talk about semantic segmentation. Very important problem in computer vision. It has its own context in medical imaging and more so in robotics, because you want the robot to tell you about the configuration space it's petroleum. So that's very important. So that's the first example. So a very, very difficult thing. So if you just even pick up this simple image and you start to do manual segmentation, you have to draw these manual contours on the boundary of the object. It's very time consuming, point number one. It's not reproducible because human beings have fatigue element, and it's a very boring exercise. So you're not excited that, okay, I've segmented one image, I'm ready for the next one. And it's not repeatable and it's not reproducible. So I want an accurate method that can be reproducible and repeatable and that can do the scene segmentation. And it's a multi-object segmentation problem because there are multiple objects in one image. The next example, again, in fact, the same example of semantic segmentation. So you have other indoor scenes that you want to mention. There is a table, there's some fireplace or stove or whatever. There are some windows, there are some lamps. So you want to cluster or segment these objects as finely as possible and as much detail as possible. So you understand what is the content in the. And this one image that I'm showing on the right is basically a chest X-ray. And what you want, these chest X-rays are done, CTs to diagnose people they're normal or they have tuberculosis or they have any malignancy. So you acquire these low dose X-ray CT images. These are actually 3D volumetric images. And what you want to segment the lungs, you want to segment any abnormality, and here you're also segmenting the heart. And again, it's a very time consuming problem with poor reproducibility, poor repeatability, and you want to have an algorithm that is automated enough which is either fully automatic or with minimum user interference, that it can segment as accurately as possible my organs in an image and any pathologies that I'm interested in. So again, so the same thing, so the semantic segmentation, so semantic segmentation in computer vision is the same like organ segmentation or multi-organ segmentation in radiological imaging. That's the first example. The second example comes from text recognition. And we have this snapshot from the MNIST data set, which actually contains, I think, close to more than 70,000 2D images where you have handwritten digits from 0 to 9. And they're written by like close to 250 people. They are coming from different backgrounds. They have different handwriting schemes. And you want to have an algorithm that can automatically detect what sort of digits are out there. So you could have some like you could have these postal mails which have these, let's say, PO box numbers or postcodes, and you want a machine to automatically tell you what is the postcode, rather than a person stationed there who has to go through this whole mechanism of reading these different handwritten notes and try to infer what these digits actually are. So we have like these kind of digits, and we can see that sometimes 7, this is also 7, this is also 7, probably this is also 7. Now this 7 is very different from this 7. Another thing is that if I look at this 9 is quite oriented. And this is again a 9 but with a different orientation. This is more thick here. And you can see variations depending on writing schemes, depending upon the sort of a pen or any marker that a person has used. And they have different orientations. So I want to have an algorithm that can automatically tell me when it receives this 2D image, what is the number on that image. So that number is 0 to 9. So it's a discrete label, multi-label problem again. So that's what we have in text recognition. Another problem we have is speech recognition. So you have speech which is embedded in noise, and it could be a single speech embedded in noise. It could be multiple people. You have an audio file you have input into a computer or a program. It has multiple people speaking. There's some background noise, disturbance, perturbations, and I want to have an algorithm that can sort out different people talking in the speech. So I want to demix my audio signal into different source components. So this is coming from person 1, this is coming from person 2, this is coming from person 3. So this demixing of an audio signal, or just to recognize the speech content in an audio signal that has noise, that has disturbances. So that's again, it's a machine learning problem. I have a very good algorithm that I can use, and it can have all sorts of applications, both in real life examples and also in defense mechanisms also. And like, for example, whenever we are talking over a phone and you have an operator